Okay, so uh, just to remind everybody that Monday we won't have a lecture again. So we made Monday the November 3rd's lecture and Monday November 10th's lecture up here. Did everybody that didn't attend the lecture on last Friday watch the video for the projects? Okay, hopefully you did. There's a chance I'm going to have to miss one more lecture this semester, and if that's the case, I will probably make it up Friday, November 14th. I know you may not like it that I keep making up lectures instead of just canceling them, but I want to make sure you get your money's worth. Why can't he just leave us alone? Why can't he cancel them? All right, so let's go talk about LT Spice. And I want to do two things. First off, answer the question that something was missing in Chapter 9 so that if there is, I can fix it and repost the zip. So let's view list. So tell me which simulation to open. So it's not used in any of these? I just downloaded this. All right, what was the other issue? The one that all the email was flying around about? Let's not. Let's put it in Chapter 7 and troubleshoot and find out what's wrong. Sound good? So I don't remember what the question was, so tell me what. Well, tell me how it doesn't work. Tell me what to do. Okay, okay, you're 7.3 and 6.19. This one or this one? This one? All right. Okay, so I got a big problem right now. First off, these are all referenced in the other directory, so I'm worried that there's going to be a problem with the referencing, but let's find out. Okay, so you want me to copy this into here. Okay, so let's go, just because I see what's going to happen here, and go do the following. All right. So now get rid of, get the scissors out, get rid of that stuff, get rid of this. And get rid of this. What next? So let's go make this look a little bit less, where's the move? Less painful. And then zoom in here. And this should be V out. Alright, just to make sure I didn't label two things V out, let me highlight the net. Okay, that looks good. And then this should be V2. You don't want a race condition, do you? If you clock the comparator with phi1 and you clock this with phi1, they're right next to each other. You want it with phi2, so you get, well, half a clock cycle, right? Yeah, but you're using ideal components. In real life, you can't put things like that, or else you'll get clock timing errors. It's like two things happening at the same time. Sometimes if something races through, it'll make an error. Why do that? Why not wait a half clock cycle? Okay? If you don't understand that, we need to talk about that, because that's fundamental digital stuff there. If you do two things at once, and it's ideal, it might work. If you do it in real life, it's very likely that unless the setup times are such, it won't work. But all right, what's the anything else? Nope. All right, what next? Well, wait. Let's hit File, Save As. Poke the running man. We don't need to change the timing. What do you want me to plot? Plot via? Okay, there's going to be a delay. It's not working? I don't know, man. So would it be evil if I copied the reference cells from chapter 6 into chapter 7? So if there was a typo in the ones in chapter 7, it's now removed. Then I re-uploaded the zip file, and then today when I come in that we're looking at the actual chapter 6 stuff reloaded into chapter 7. Would that be evil? So when you guys tell me, I'm like, well, one of the cells has a typo in it. Well, that's easy to fix. I'll just copy the ones from 6 over into 7 and upload them again, and it'll be fixed. But I didn't verify it. So now it's fixed. No. There's something, a typo in something in one of these components that's messed up, like a short or something shorting or something like that. Is it working now? No, I just fixed it right before class. Because I went in, I'm like, okay, what were they talking about? And then I looked, and Yeon said, no, use the symbols from 6 or something like that. And then you guys said that earlier, and I'm like, okay, well, let me fix that. I copied the symbols from 6, overwrote what was in 7, and uploaded the file. Boom, I'm done. Took me like 2 minutes. No? All right. I guess you could simulate wrong. Any other questions or comments now that I had my fun? Yes. 240. So we're done here? Are we done with LT? Oh, 240. All right. I'm glad to see you're looking at the book. K8 in this schematic. Let's look. No, it's 8. Right? Wait, no, this is m equal to. Oh, so we're decimating. This is like m equal 2 and the k equal 8, so km equal 2 times 8 or 16. Is that what we're doing? So that would be the decimation filter from, let's see, page. Wait a sec. So this is Oh wait, no, this is, we want decimating, so this is 1 plus z, so there's 2 of them. And then this is, well, it's this figure right here. Let me pull it up on the doc cam. What? So if I was really evil, you know what I would do? I would say, I don't know what's wrong with you guys. So we have 2 stages, or it is 2 stages, right? I already forget, have a senior moment. So we got 2 of them, and then another 2 of them, and then the hold register. And so we have L is 2, then we have another stage, L is 2, and then we have a hold register. So this is log 2 of stage, so we have, if 8, that would be, what's that? There's 4 stages? Oh, so this would be, if L was 2, that would be 2, and that would be 2, 4 stages. So K is 8. 240. Uh, 7 point. Oh, okay. Okay, so this is 16, so using 4 stages, L equal to the increase in resolution in each stage is 2 bits. See, when L is 1, the resolution is 6.14 bits, round up to 7. Because the output of the digital filter is 9 bits, 8 bits through the 4 stages, plus 1 bit coming out of the modulator, we drop the lower 2 bits, divide by 4 to get the 7-bit resolution. So for 16, that would be 2 to the 4th. So plus 1 bit. So the rounding is a little off. Is that what you're saying? So like in that, it's not. Wait, this doesn't work? It doesn't match the sim? Wait a sec. First off, this is for cake 8, not 16 like the example, right? What? Yeah, but hold on just one sec. But isn't it want you to use 16 here? And then that's 8. Oh, this one's 16 in the simulation? Oh, okay. All right. All right. The resolution calculus 600, which we. Well, you don't. If you throw that lower bit away, it it doesn't really change things, right? I mean, I can get rid of it and it'll basically be the same, but it's there, so why not use it? Wait, you don't want to get rid of this bit. You want to get rid of the bit down here. Yeah. Well, you can think about it. It's only, it's not going to be that different. So let's hit run. You can't mess with the MSB because then the scaling changes. No, no, it's the maximum range. It won't ever get to the point because of the limited input. It won't ever get to the point where you get this bit going high, except for if you put in like, it won't work if I put in here like VDD, if I remember correctly, it'll overflow. But if you keep the input range limited, then it won't overflow, and it's just a way to scale. So this, don't get confused with this. This is just a scaling of the amplitude. But again, if you put in a full level here so your output's always 1, then it's going to overflow. But so this is 1, 2, 3, 4, 5, 6, 7. This is just scaling, right? I can move everything up and say, oh, I threw away the 2 LSBs, you know, the B2 and the B3, but then the scaling doesn't work in the filter. That's fine. You're just scaling it so that it's full scale. No, but you are throwing away the LSB here. You're moving it so that, I mean, again, I can move this up, but the scaling won't work out. Because remember, in all those sync filters, it's not really just the 1 minus Z to the thing. You have to divide by a scaling to make the words match. Okay, so there's always that factor where here I'm throwing away this one and this one, but I'm actually rescaling it here. So I'm multiplying by 2 so I get the right output. So that's why I shift it right. If you don't do that and you look at the output, it's not going to be scaled correctly. Yeah. Yeah. So this one will work. It's going to be the same. And if you go, what? No, here, let's show. The problem is, uh, uh, what's that? Oh, did I move those two? Ugh. It won't be scaled properly, but if it might even overflow, but here, let's find out. Well, if they're noise and they don't increase the resolution, they're just random stuff. So it doesn't buy you anything, so why propagate them? Yeah, you're not really gaining any resolution. It's just a random bit that comes through. So, yeah, you're limited by the signal to noise ratio. I don't think it'll influence its random, so maybe a little. But I mean, you don't want to propagate through because it's extra hardware. So we'll do one more sim and then move on to today's discussion. But before I do that, does anybody have any questions? Have you started on the projects? They're easy? Too easy? Yeah. All right. It's like watching paint dry. What's that? Yeah. Looks like there may be some problem with the common mode voltage. But we'll see. We'll see what happens in a moment. Actually, let's see if we can do it right now. Which is what we did by shifting. Let's see if it saturates. What's that noise? All right. I guess you can see here the decimation is by 16, because if the input clock is 10 nanoseconds, the output clock will have a period of what? Looking at the waveform. If the input clock's 10 nanoseconds, what's the period of the output clock looking at the 160? You can look and say, oh, from here to here is 160 nanoseconds. Oh, from here to here is 160. 160. 800 roughly to 960. All right. let's stop. And any last second LT Spice questions? Yeah. Probably. That's why you have the timing's importance. That's why you don't clock you when you're clocking digital signals and they're high speed and you clock something, you make sure when you clock it that that edge is away from anything moving. Okay, that's the simple-minded way to think of it. Is if I'm going to clock a flip-flop, my input's got to be not even remotely moving when I clock it. Okay, so if you clock Phi1 and Phi1, a lot of times in real circuits there's a hold setup time and you can get away with it, so it's fine. But if you're using ideal stuff and there's issues with like the output of the comparator when it actually changes states, it's going to fail every time and you're going to waste time. So you got to use a clock phase that's right before the Phi1, say, so you have a whole clock cycle. Does everybody follow that? Because if you don't understand that, you're going to waste a lot of time on the projects. The digital clocking, you could design everything right, but if you don't get your digital words out, your project's not going to work. So in my mind, I keep thinking, oh, digital's easy, and then I find out, no, it's not. And I ask things like, I'm doing my ALU project right now in my lab class. They're challenged to add and subtract numbers. So, sure, let's live it up. Yes. All right. No other questions, project, anything? Because we're going to talk about today integrator, op-amp settling time, op-amp offset, op-amp input referred noise, and then practical implementation of the first order noise modulator. And then we're going to have a little quiz for a grade booster. And what was lecture was this one? Lecture 21 and 718 November 5th. And let's go. That was section 718 if I remember correctly. And what? Lay it on me, man. Yep. Yeah. If you increase the gain of the integrator, the op amp, then the performance should get better if you don't also kill the speed. Because if you kill the speed of the op amp, then there's going to be problems with improving the performance. Okay. The integrator saturating. What that means is you need a larger feedback capacitor, or you need less signal fed back. So if you're doing the continuous time, you need to clock the switches in series with the resistors closer together so you're feeding back less signal. So basically, it's very simple. You either need to increase the bucket in your integrator, or you need to reduce how much you're feeding back to keep it from... that's way too big. Oh, okay. I don't know. Maybe I assigned a project that can't be done. uh, uh, and then this is, I wonder when I'm like 80 and I look at those videos, I'm going to be like, you remember I used to remember that stuff. All right, so this is integrator gain, right? Or no, op-amp settling time. And this is related to bandwidth, so this should be a good thing. And this is section 7.1.8. And before I want to quickly review the performance of the op amp, and get something like this. So you're all going to help me. So I'm going to plot the open loop gain of an op amp, so I get the following. So what's the AC voltage right there? Okay, and so then I can, okay, so now everybody knows in a real op amp you can't do what I'm showing. You have to put a DC bias stability feedback, right, to put a resistor on the output, since there'll be an offset in the op amp. I don't have my gold book, but it's okay. Maybe it's not okay. Here, let me just sketch it. So instead of doing this, if you put your op amp and you want to measure this in simulations, you need to put a big resistor here, and then put a big capacitor here. Let's just say 10 microfarads. And then what happens for DC is that this voltage becomes VCM for DC, and then because for DC this is an open, all of the output is fed back and charges this capacitor, and then this voltage becomes VCM plus or minus the offset voltage. So it biases up the op amp for proper DC stability. And so then if I look at the 8, does everybody follow that? So if you're using the self-biased diff amp, you might set the DC voltage to 2.5, and then this would be a DC stability. You send it back here, and then there's issues though. Let me do it for you just so you can see, because it's not a real op amp, it's a diff amp. So let's go pull that up. Let's just pick oh crap, file, save as _AC open loop. And then let's get out the old scissors here. And I'm going to get rid of everything except for those. And I'm going to change this because it's the C5 process to 5 and 2.5. Then I'm going to go get the amp. Copy. And I'm going to take a resistor here. So what I'm trying to do, whoops, I'm trying to look at the open loop response of this op amp. So I'll put a resistor here, and let's just call this resistor 1 MEG, and hit OK. And I'll put a capacitor here, and this will be 100 micro. And then I'm going to go over here, go down, go over, press G. It's funny, in the other class I'm using different tools. And sometimes I forget and use the different buying keys, or I'll say, let's get the scissors out, or whatever. Okay, so what I'm not going to look at both out here. Why don't I, just for the hell of it, because one output will be, let's call this V out P, and we'll call this one V out M. And let's grab a source. Whoops, I don't need that. I want this voltage. And then I want advanced DC value. Oops. Yeah, we'll put 2.5. We don't need the common mode voltage then. An AC1. In an AC analysis, it always assumes small signal, so I could put 1,000,000 volts there and it would still think it's a small signal. So I'll put 1 so I don't have to divide the output to get the magnitude. Hit OK. Press G. And get the pin out here, go down. And it would be good to tie a load here. I'm not going to do that. I think in the chapter 9 I put like 400 femtofarads or some, I don't remember what the load is, 4 pico or something, I don't remember. But then I'll put, let me poke the running man and do AC analysis, decade, 100 points per decade, start frequency, and let's go 1 kilohertz, stop frequency 1 gigahertz. Okay, and plot the input. Does that look right for the input? 0 dB. Plot the output. That doesn't look right. Did I use the wrong? What? How come I'm getting so high a gain? Let's make sure that voltage is DC operating point 2.5. That bothers me. DC operating point 2.5. DC operating point. What? Why does this bother me? Yeah, it should roll off and the gain shouldn't be that high, so I'm wondering what the heck. So let me do a little probage here. Yeah, there's no phase shift either. What? How can there be that high a gain? That's because I design good circuits. Yeah, really. Oh, that's why. Thank you. It's using the default models. I would have taken some time to troubleshoot that if I would have ever got it. Save. Run. That's good, but the speed is, well, I don't have a capacitive load, so let me, what did I use in the book? 1 pico load? Yeah, I think 1 pico should be good. Yeah, or 10. But what did I use here? I want to use something that's similar to what my feedback capacitance is. What's that? 400 femto. So let's put 1 pico on there, and let me just make sure V out P here. So that's 1 pico. And ground, that'll make the speed a lot slower. It's always fast when you don't have to drive a load. Let me just push in here and see. Okay, out P's the high gain node. I kind of figured that. And even that, this is a damn good circuit, man. That looks right. There we go. So the gain bandwidth product's around, or the gain is, yeah, gain bandwidth's around 1 gig. So that's pretty good. Well, it doesn't have phase margin because there's no feedback. So it's just showing, yeah, the phase is, could be better, but it's fine. All right, any questions about how I looked at the open loop response there? Because we're going to use that right now. Okay, so I can write 22 or 26 dB is a gain of roughly, let's see, 10 plus 5 dB is, or let's see, 6 dB with 2, so it'd be 20, and it's a little bit more, so 20, 21, actually, 21, right? It could be higher with the difference in the V out P and V out M, right? Yeah. And if it doesn't, then your SNR falls off if the open loop gain isn't greater than the oversampling ratio. So here it's kind of marginal, right? Because if you look at our overall oversampling ratio, it's roughly 64. But then I don't know if, because this is new stuff, I don't know if you'd look at 64 just one path, or just the K paths, or 8. So we're going to discuss that, and you can discuss it in your reports. I don't want to tell you everything. Okay, discovery's good. So if I go, let's sketch the frequency response. So we had a gain of 21. Let's just keep it easy and say 26 dB, which is 20. And I came over here and we went out, and that was 1 gigahertz. So I'm going to do two things here that everybody should be able to do easily, especially if you took analog from me already, or 2 analogs, is I want you to determine the equation for this circuit, or for this op amp, the transfer function, and then I want you to tell me, based upon that, what's the 3 dB frequency here. So 26 dB is equal to 20. What's that? So yeah, V out over V plus minus V minus. What's V minus here, AC wise? Yeah, ground. Anybody not see that? Okay, so that's equal to 20 over 1 plus J, and of course this is a low pass filter, F over whatever this 3 dB frequency is. How do I know what that is? Well, what's the slope here? Yep. So if I go to 100 megahertz, what's the gain? 20, right? Or 20 dB per decade is the same as minus 6 dB per octave. So if I go up to 26, which is right here, that means what's octave? No, 2. So divide by 2 or multiply by 2. So I would go up to, we'll verify, see if I'm right. And if I'm wrong, you can say wrong. Okay? So we go up to divide by 2, and we go up to 50 megahertz, and we say this is 50 megahertz. So it would be divided by 50 megahertz. So this is the low pass response. Does everybody agree with that? Let's go back and look at our simulation. Get ready to say wrong. Where was that? What did I call it? Oh, okay. Run. And 3 dB. Here, let's put it in dB. I don't think you're going to be able to say wrong. Whoops. What did I hit? No. And 3 dB would be 20, 623, so right around 23, right about there. I would say that's pretty close to 50 megahertz. Would everybody agree? Right. All right. Any questions on this? Okay, so and this will be related to what we do in our integrator gains, but I want to talk about the settling time. Questions? Okay, so let's go back. Sure. And based upon this equation now, I want you to estimate the settling time. So I have the following circuit. And let's put the same load, because of course those characteristics will change with the load capacitance. And I want you to, let's say that we go from 2.5 to 2.55 with a pulse. I want you to estimate what the output looks like. Well, I know that V out over V in the frequency domain is equal to 20 all over 1 plus j f over 50 meg. Okay, whenever I write this, I think to myself, holy crap, would I cry and be unhappy if someone in this class didn't understand what this was, or couldn't take an RC filter and derive this. Okay, so what's the feedback factor here? How much of my output am I feeding back to the input? All of it, so beta equals 1. And we know in a simple feedback circuit that the closed loop response is equal to the open loop response, which we have right here, divided by 1 plus beta AOL, but you just told me that's 1. And so would everybody be cool if I wrote that as what's that? No, well, I don't want to say approximately 1 because I want to estimate what the frequency response is, right? So I'll go ahead and put 20 divided by, I'm going to do this in 2 steps, 20 plus 1 plus f over 50 meg. Oops, I left out the J. Did it get lighter in here all of a sudden? Ooh, ghosts. Classroom's haunted. Okay, so what am I going to do now? I'm going to say that's approximately 1. Okay, so that would be 20 divided by 21. So the gain's not going to be exactly 1, 20 over 21, but I'm going to say approximately 1 instead of 20 over 21 divided by 1 plus JF over 1 gigahertz. Okay, so tell me what's the deal with the 1 gig? Yeah, that's the gain bandwidth product. I go back, I look. Oh, that's right, I forgot to save this. Whoops. Hit save. I go back here and I say, oh, I'm roughly at 1 gigahertz. And if I put the op amp in the unity follower configuration, it would be a gain of 1 and go out to 1 gigahertz. If I put it in a gain of 2, it'd be 6 dB and go out my bandwidth here. So I would just divide 1 gig by 2 and get 500 megahertz, etc. So my gain bandwidth product is 1 gigahertz. That's what I'm showing right here. All right, so now, are we ready to estimate the settling time? Okay, so tell me what to do. All right, so let me ask this. If I have the following circuit and I ask what is V in over V out AC wise, what's the answer? One over 1 plus J F over 1 over 2 pi RC. Does everybody agree with that? If I come over here now and I put a step in and I ask what is the equation that relates the step to the V out, you say, oh, V out is equal to my V in step, whatever, 0 to V in, times 1 minus e to the minus t over RC. Does everybody agree with that? Okay, so then I go, oh, well, then this is the exact same deal except I have 1 over 2 pi RC is 1 gig, and this RC, or I could write this as tau, is then I get 1 over 2 pi times tau equals 1 gigahertz, which equals, which says tau. Am I losing anybody here? So I take the 1 gig, the 1 over 2 pi tau, where tau is RC. And for this equation, I get 1 gig divided by 6.28, which equals 159 picoseconds. Am I losing anybody? It's good? So then I go and I ask, oh, okay, so then V out is equal to the step, in this case 50 millivolts, times 1 minus e to the minus t over 159 pico. What's that? I didn't. Tau is, oh yeah, thank you. You know, I'm nowhere. What? Oh yeah, thank you. You know, I know where I'm going, right? So let's see. 1 over 1 gig times 2 pi, which is 1 nanosecond over 6.28, which is 159 picoseconds. Keep me honest, man. All right. So now this is my equation. I want to talk about that. So if I look at, let's actually, before I do that, well, does anybody recall, especially if you took 421, 621 from me, what the delay time would be just looking at that? What is it for an RC circuit? 0.7 RC. Okay, well, I'm going to talk about that more in a moment. But if I do this simulation and I look, I should see 0.7 times 159 pico is the delay from my input to my output going high, or roughly 105 picoseconds if I did the math right in my head real quick. So why don't we do this sim real fast and see if I'm right? I'm guessing that from the input transitioning to the output going high is going to be about 105 picoseconds. So let's go back over. New files, save as, and do and let's see, let's change this one from a pulse. Let's go initial 2.5, V on 2.55, delay, let's go 1,005 microseconds, rise time 1 picosecond. Why did I use 1,005 microseconds for the transient simulation? Well, yeah, I let it go for a microsecond because when you do a transient, it's like you apply the power. When you, oops, thank you. You apply the power, and then you got to let everything settle before you pulse it. So if I pulse it right after the simulation starts, the power's just been applied and things haven't reached steady state. I could probably get away with 50 nanoseconds in the sim, but let's just do this, okay? Any questions about that delay? So hit OK, get the scissors out, get rid of this, get rid of that, get rid of this. Right click on this, go to transient, stop time, let's go 1008 nano Time to start saving data, 1000 nano, because I don't want to see all that stuff at the beginning where it's powering up. Any questions? So I hit OK, then hit save, and I poke the running man, and just to make sure my pulse looks right. Notice that if I don't put the right pulse in there, it could start out so the op amps or the amplifiers not turned on. Like if I started at 0 and went to 50 millivolts, the NMOS on the input of the op amp wouldn't be turned on. So I got to start where voltage. Now, one thing I know I'm going to have here is I'm going to have a bad offset. We talked about offset last time, I believe, and how it's referred back to the input through, or actually is added to the input. Okay, so let's see how bad the offset is. And what was my delay? It was estimated at 0.7 RC, or 0.7 tau, which is roughly 106 pico. How do I know I'm going to have bad offset? There's no output stage. You look here, this guy has to feed back up to here. So it's wired to there. And then the open loop gain is only 22. So it's not going to have a good offset. Yeah, there's no output buffer here. So it's to make it work with such a low gain, it's going to have a bad offset. So I say that, and I assume everybody knows. So when I look at the pulse, what am I going to see if it has a bad offset? It's going to be shifted one way or the other, right? So DC-wise. There it is, shifted. And you know what? Let me run the sim again, and let's start collecting data at 104. Hit OK. Hit save. Hit roll them. And let's go to, how about 1.6. You see a little bit of feed through, that fast feeding through, and then I guess the delay time, let's go get rid of that offset, so let's add 4 millivolts. Oops. 4 millivolts. Oh, I need way more than that. I need 36 millivolts. 40 millivolts, let's put. And let's OCD it. Alright. And I estimated 105. Go to the halfway point. Pretty close. Depending on how I move my cursor and where I put my cursor. I think that's in the ballpark. Are there any questions about what I just did? Does everybody understand what's going on? Any questions whatsoever? Yep. Path delays, the indecision in the comparator added with the feedback delay through the resistors, which through the resistors should be 0. That's basically it. Because once you get to the forward path, then that's not a feedback path delay, that's a forward delay. All right, so let's let's go look at the book, and specifically let's look at, what was our beta here? Was 1. Here, when we have a feedback, you see our beta is not going to be 1. It's going to have some feedback factor which will influence the gain. So now when I write these equations, and I write V out equals V out final times 1 minus e to the minus t over tau, and then tau is equal to 1 over 2 pi, the unity gain bandwidth, which was what in the op amp we just looked at? 1 gigahertz, that's the gain bandwidth product, and then you can also show that that's times beta if you go back through the math and don't put beta equal to 1 in that previous equation right here. Okay, Does anybody have any magical not understanding what's happening here? Okay, so beta is equal to this. And then if you look at the percentage that you get V out. I'll just write the step size here. I'll do a little different than the book. Is V out is equal to V out final times 1 minus e to the minus t. And then I'm going to plug in here the 1 over 2 pi f unity, where we'll do it 2 pi f unity times beta. Except for a clock system, how long is t? How long does that op amp in what we generally talk about have to settle? Yeah, ts over 2. So this we'll put as ts over 2. And if we plug that in and we make some assumptions about the, well, t has to be settled in ts over 2, we can get some indication for the gain bandwidth product. So what I'll rewrite this as is V out is equal to V out final times 1 minus, would everybody be okay if I wrote this as, if I rewrote this as 1 over 2 f sub s? Okay, so then I'm going to plug all this in, and I get e to the minus pi, so this flips up, times beta, whatever beta is, times the unity gain frequency. The 2's cancel over f sub s. Does that make sense? So that's why I wanted to go through all the examples in the op amp configuration. So if I look, I can modify the equation in the book for the z-domain representation by adding this gain term. And before I go through anything else, so this is the integrator response, right? And then this is a gain error. Let me make a couple. What's that? Hold on. So
TS over 2 divided by 2 pi, like dividing by something is the same thing as multiplying by 1 over, right? So TS over 2 multiplied by 1 over 2 pi f unity beta, and then 2's will multiply by cancel.
Yeah, why is that? No, that makes total sense here. So if let's do this. If it's minus t divided by 1 over 2 pi f unity times beta.
Oh, okay, yeah. You
Right.
have 1 over 2 pi in the green pen.
Oh, yeah, thank you.
Okay.
Yeah. Again, know where I'm going. So the point here is that you modify the integrator by this term. And now I want you, if you've been daydreaming, I want you to follow what I'm about to say. So what this says is that if I have a consistent error in my gain settling, which means if I consistently, instead of dumping the whole cup out, I only dump part of it out, but every time I dump it out, I dump the same amount out, meaning I go clock the integrator at the same time and I have an error, it doesn't settle, it only gets to 67%. It shows up as a change in the integrator gain. Okay, if it shows up as a change in the integrator gain, that can be compensated for by the comparator, right? Because remember, then the input of the comparator shrinks because the gain of the integrator drops, and then the gain of the comparator goes up because it's the 1 VDD divided by the input. So this is really important. It says, hey, if your op-amp doesn't fully settle in this topology, it's not a problem as long as it's nice linear settling like this. It is a problem if you have slewing. Okay, so if you have slewing, which means the integrator's not behaving like a linear circuit, it's behaving where there's a current source charging the capacitor, then it's a problem because the length of time will depend on how much you're slewing. So if your integrator output slews, that's bad. Does everybody understand what I mean by slewing? I'll show you real quick with a simulation. So if I look at the transient here, and you see I get this nice RC response, and you see the gain error here, it doesn't go all the way up, and if I clock the comparator, if I clock and I get another input sample and it arrives here, I haven't fully settled, but it just means there's a gain error in the integrator. If I go back here now and I make this 100p, this is like an RC circuit charging. If I go back and do that, and I hit OK, then I hit run. The stupid circuit's too good. Let's go. And I get something like this. You see how it's linear? And if I look at what's happening, if I look at the current that's charging, it's essentially constant. It's not like an RC. So when I have linear current charging a capacitor, I get slewing. Okay, and so I don't want that to happen. So if it's not slewing, then I'm fine. Delete data file, yes. Okay, so does that make sense to everybody? So if you go look, the whole point here, oh, I'm designing my projects and my integrator, I just can't get it fast enough. If it's not fast enough, but it doesn't have slewing, or it has a gain error because the op-amp gain isn't high enough, it shows up as this constant term here in the response, and the topology still should work. Okay? Any questions? I got a question. In this RC circuit, or in this circuit here, or in the one I derived, does my delay time change if I change my input amplitude? If I go from 2.55 to 2.51 or 2.56, is the delay going to change? Does the amplitude influence the delay? No. That's the whole point. That's why this is a constant term. Okay? It's not, the input amplitude's not seen there. Any questions? If it was slew rate limited, then it would be a problem, because that means like every time I'm feeding a signal back, it depends on how big the signal I'm feeding back is to what's fed back. Okay? All right, we've talked about op-amp offset already. We've talked about input referred offset, but we haven't talked about input referred noise. And basically, the input referred noise is divided by the gain of the integrator and adds directly to the input signal. The benefit is, and we go through here, is that if that noise has some spectrum and you pass the noise through a averaging filter, you get a reduction just like we did with the quantization noise, because you're filtering out part of the noise. And so if the noise is a white noise, meaning it has a flat spectrum like white light does, then your RMS noise, the standard deviation, is reduced by the square root of the number of samples that you're averaging. So that makes it so that noise becomes, the more samples you average, less and less of an issue. And then finally, because, well, two reasons. One, well, the main reason is because input signals can get corrupted by noise. Your input signals in practical modulators a lot of times are fully differential. And so if you have noise feeding into the inputs, it feeds into each equally, and so it subtracts out. So an example of a modulator is seen right here, where you have a fully differential signal path that feeds everything back around. Okay, so this is nothing more than of course, It's nothing more than what we've already looked at, just in fully differential form. Does anybody have any questions? Does anybody have any answers? Answers are better than questions, especially if I don't have to answer them. All right, let's take our little quiz. Let me kick the video off real quick. Today is so no class on Monday, everybody knows. And today is this video right here.